Hello everyone, good morning. My name is Daniela Gottesman, and my research has to do with the analysis of neurosignals and specifically looking at their shapes. Now before I get into the details of my research, I want to give you guys a little bit of a background and an application as to why my research is important. So about 1 in 50 Americans suffer from paralysis. And as you may know, people suffering from paralysis often have normally functioning brains. The problem is in the past that neurosignals travel to get from their brains to the rest of their body. And in order to help them gain more independence, we have created devices called brain-computer interfaces that can be powered solely through the brain. But in order to build these devices, we need to understand how neurons communicate. And to do so, we use devices called multi-electrode arrays, or MEAs, that record groups of signals. And what these devices are just chips that have electrodes plated on top of them, and the electrodes measure neurosignals between groups of neurons. But commercial MEAs have several problems. The first of which is when they're placed into our brain recognizes them as foreign objects. And so an inflammatory response is induced, which causes the formation of scar tissue. And you can see that in this picture. And the scar tissue forms around the electrodes and prevents them from detecting signals. Another problem is that the electrodes on the MEAs are very brittle. So whenever we move our head just a little bit, that's enough to break the electrodes completely or cause small lacerations in our brains, and we don't want that. So what my lab did is we made an MEA that has both flat electrodes and electrode pillars. And what's special about the electrode pillars is that they are made out of polydimethylsiloxane, which is just a flexible rubbery material that allows the electrodes to bend with brain movement. Another advantage of the pillar electrodes is that they are three-dimensional and they can detect neurosignals in 3D, which is really important because neurons grow in three-dimensional structures, and so we might be missing out on some information if we're recording them in 2 dimensions. Okay, so the overarching goal of my project is to better understand how neural networks work, and how I'm going to do that is by making an algorithm that detects neurosignals and then further categorizes them based on their shapes. And I want to see if the pillar electrodes detect more kinds of shapes than the flat electrodes. Okay, so my algorithm has 2 main objectives, the first of which is to differentiate between signal and noise. And what noise is just any sort of background sound that gets picked up that we don't want. That's just junk. And this is the part that we're interested in, the signal. The second part is categorizing the signals based on their shapes. And the things that we look at are the peaks, which are the most extreme points, and we look at whether they're positive or negative and how many there are. And that tells us what kind of shape the signal is. Okay, so the first thing in detecting a signal is the algorithm runs on all of the data and checks if the voltage at some time crosses the negative or positive threshold. And if it does, then that's interesting to us and we want to look further. But if it doesn't, then it just moves on to the next point and checks the same thing. So let's say that it did cross the threshold. Then we want to find that peak that I talked about before. And it just looks over an interval of about 10 time points and finds that peak. And once it does, it stores it, and we end up with this list that looks like this of just all the voltages of the possible peaks that we have detected. The algorithm then takes that list and it starts categorizing the peaks based on their time points. So let's say if 2 peaks are within 25 time points of each other, then they're probably in the same signal. And so we group them up into these little chunks here based on their time points, and each of these chunks represents 1 signal. But we're not quite sure that all of these peaks are actually peaks. There might be noise, because what can happen is that we get these little fluctuations right here, which the algorithm detects as peaks, but they're actually not. They're just noise, and we want to get rid of that. So once we get rid of them, we want to further categorize them. And we use a binary categorization system. It sounds complicated, but it's really not. All we do is that it looks to see if the voltage is positive, and if it's positive, it's given the value of 1. And if it's negative, then it's given the value of 0. And so instead of having this mess right here, we're left with this clean list here that we can now analyze. The next thing we do is we just play the matching game. So we go through each signal here, and if it matches the definition of one of the categories here, then we know that signal is part of that category. Okay, so after we ran this, we ran it on about 20 files of 30 seconds each. And we got we created this diagram here where each green region represents electrodes in the control regions of the flat electrodes, and the blue region here represents the electrodes in the pillar region. And you can see here visually that it looks like the flat electrodes actually detect more waves than the pillar electrodes. So we wanted to look further, and we did a statistical analysis. And we actually found that we can't make a conclusion about this because the standard error was too high. Okay, so I spent the first part of my talk telling you how good pillar electrodes are, but I actually didn't find out if they're good. So one reason this can be is because the PDMS, or the flexible material, might be preventing the nickel from conducting electricity, so it might not be detecting all of the signals that it touches. Okay, so in the future, I want to run my algorithm on more files, and by doing that, I can start optimizing some of the algorithm variables. And what I mean by that is, before I said that if two peaks are within 25 time points of each other, then they're probably in the same signal. But I want to see if that's the right number I should be using. Another thing is I should possibly add more shapes. If we look here in this graph, this represents all the unclassified waveforms that didn't fit any of the categories. And we can see that some of the shapes here are reoccurring. So that might be an area of interest to see if we want to add in more shapes. And then another problem with the algorithm is that it picks up high frequency noise. So this noise here does cross one of the thresholds, but it gets detected as a peak, and that's wrong. We don't want that. Okay, I'd like to lastly thank my mentor for everything. She helped me outline the algorithm and make it and understand everything. So I'm really thankful for that. I'd also like to thank my TA Selvi, for helping me edit and format everything, and for Lena for looking over everything as well. I'd also like to thank all of the RMP interns that worked with me and supported me, and Luke, Theo Garjon, who's the principal investigator, and the research mentorship program.